our next theorem says if f is a continuous vector field, then the line integral of f dot dr is independent of path in a region D if and only if f is the gradient of some potential function little f defined on D. So here we're saying that line integrals are independent of path if and only if our vector field f is conservative. So that very first example we did in the last video, you can go back and check, and that vector field xy is conservative. And so that is why that line integral was independent of path. Okay, so what I want to show essentially is that path independence of line integrals is equivalent to our vector field being conservative in that region D. So we actually have to show two things. First, we have to show if capital F is equal to the gradient of little f. So if my vector field is conservative, then the integral of capital F dot dr is independent of path. But in fact, it is independent of path because we can apply that fundamental theorem for line integrals. And that is clearly independent of path. Because it just depends on the endpoint. Okay, so essentially we already proved half of this theorem. We already proved that when you have a conservative vector field, then if you integrate it, it will be independent of path. But now we want to prove it the other way. We want to prove that if we have a path-independent integral, then our vector field must be conservative. Okay, so to show this, what I'm going to do is I'm going to define a function, and that function is going to be my potential function. Okay, so let me define this function to be equal to an integral over the path C1 of f dot dr plus another integral over a different path C2 of f dot dr. So I'm going to define f of xy to be the sum of two line integrals, but let me show you what those two line integrals are going to be. So first of all, I'm going to have to come up with some fun region here. We'll call it D. So this fun region here is D. Okay, and then we're going to give this some sort of starting point. We'll call that starting point maybe x0, y0. So that's going to be a starting point. And then what I'm going to do is I'm going to integrate, or I'm going to, integrate along a path like this. And I'm going to make that path stop. So that'll be C1. And then I'm going to make a horizontal line segment here, C2. Okay, and those two paths are going to connect x0, y0 to xy. So very important that C2 here is horizontal. Okay, so there's going to be some intermediate point that we get to, and that intermediate point is going to be say x1, y. Okay, and then these two y's are the same. Okay, so that's how I'm going to define my potential function f of xy. It's going to be the integral from across this c1 of f dot dr plus the integral across c2 of f dot dr. And notice it is a function of x and y because the integral ends at the point x, y. And so you can imagine that I can move around the point x, y, and I just have to change what my paths c1 and c2 are, making sure that c2 is always horizontal. Okay, so what is df dx in this case then? Well, df dx, okay, is going to be the derivative of just c2. And that's because this first integral, the integral of over c1 of f dot dr, is constant with respect to x, right? Because the endpoint for this path of c1 is x1, not, and it doesn't depend on x, okay? So only c2 depends on x. c1 depends on some intermediate point x1. So the derivative of that first integral is going to be 0. So the derivative of f with respect to x is just the derivative of the second integral. Okay, but let's notice something here. The integral of c2 of f dot dr, right, we can write that as just the integral of c2 over of p dx. Okay, so something that I did not mention here is that maybe f should have been listed as being pq. So here I'm going to let f be pq. So p is the first component, q is the second component. Okay, so if I integrate c2 f dot dr, it's just going to be p dx. And that's because there's no change in the y direction over c2. So the dy in this case, which is going to be like y prime of t dt, that's going to be 0 because y prime of t is going to be 0. There's no change in the y direction. Okay, then if that's the case, then the derivative with respect to x of c2, the integral of c2 f dot dr, is just going to be my function p of xy. Okay. That's interesting. Well, then we can play this game again. So we can draw different paths and everything and play this game again that we just did. So maybe define f in a slightly different way to show that d dy of this integral c2 over c2 of f dot dr is going to be q of xy. So we would essentially have to define a different path, okay, maybe one that looks like this, and then we approach the point with a purely vertical path, like you can see here. And if we do that, then we can show that d dy of the curve integral of f dot dr over C2 in that case is Q. So I'm not going to go through all the details, but we can basically do the same thing to show that. Okay, well, what does that mean? Well, then okay, what have we shown? We've shown that the gradient of little f is PQ. Oh, but what is PQ? That's capital F. And so that means that we have a conservative vector field. So if we have this path independence, okay, then we can show that the gradient of this function f that we've defined to be our potential function is in fact our vector field capital F. So that's kind of a fun little proof of that theorem.